Phil. I'm Jonathan Abrams, not Adam Williams. You probably can tell. And you can probably tell because I'm wearing a suit. I don't get on the tools very much. But anyway, I'm here to sort of set the scene, I guess, for the main, for one of the main parts of tonight, and that's really to talk about the alternative fuels and where we're heading in that direction. It will cover some of what we're doing today, most recent IMO meetings and some things that have come out of that. And we'll talk a little bit about some practical application of alternative fuels and what we're seeing not only in Australia, but regionally and also globally as well. As I said, it is to set the scene so that when Adam comes up and can talk more about the engineering, the structural side of alternative propulsion systems, if you like, and fuels, it gives a little bit of a backdrop on why this is happening a little bit faster now than it has in recent times. And there's no doubt about that. Let me just... Yeah, okay. Okay. No. All right. Technical glitch. Let's go for it now. Okay. Okay, so this is actually a picture of the IMO meeting room in, I think it was May this year, the Maritime Environmental Protection Committee, number 74. It was there deliberately to look at, amongst other things, the goals of reducing emissions from global shipping and ways to do that. It's been a long time in coming, and I think everyone will know that on the 1st of January 2020, we will, the globe will actually have a new level, upper limit of sulphur in heavy fuel oil of 0.5%. Down from 3.5%. So it's created some ruction within the shipping segment, and quite literally this was what was happening outside the meeting of the IMO about sulphur. There was a little bit of scaremongering about it. We'll talk a little bit about how reality doesn't always mimic theatre, but we thought it was a nice way to introduce two delegates showing up there. You know, the seriousness of what we're talking, or what was being talked about in London. So, what we're talking about here is the sulphur 2020 cap. There is no delay in implementation. Again, to put it into context, I think this was first discussed in terms of lowering the global sulphur limits from where they were back in the 2000s to 0.5 or thereabouts. About 2005 it started. I think 0.5 was proposed maybe in 2008. It's dripped along forward like that. So unfortunately, some people have left it a little bit too late to get prepared for this, and the business and the impact it has on their business will be more profound if they hadn't because they've started so late. Excuse me. So as I say, it will be 0.5% maximum unless you have a scrubber, an exhaust gas scrubber system fitted to your vessel. That also means that there'll be a carriage ban for non-compliant fuel from the 1st of March. So up until then, unless you have an approved scrubber or you're transporting it as cargo, you will not be able to take HFO on board. And there will be quite a lot of effort put into enforcement and compliance on those things. It will be important, I guess, in this run-up to the end of the year and certainly first quarter next year, that there's a lot of dialogue continuous between ships, ports, suppliers and authorities as well. AMSA here have said there will be no exceptions. There will be a transition period, learnings, but I don't think anyone can expect that there'll be an AMSA surveyor on every ship on January the 1st checking that they've got compliant fuel on board. But it is something that they're going down the path of. Excuse me. The other ones, I guess, is that apart from compliant fuels or scrubbers, alternative fuels come into play there. So LNG is a viable option and those sorts of things, amongst others, which we'll talk about a little bit about in a moment. So some of the outcomes, have the regulations been fast-tracked? I guess the answer is yes to some and no to others. As I say, it has been a long time in the coming. Anything that goes through IMO needs a lot of lead time to get accepted, and then to be passed into law, if you like. But as I say, one of the other things that they're looking at is at MEPC was, with a view to reducing global emissions, what are some of the things that can be done by ships, by flag states, by the industry in general. And they're looking at setting in place short, medium and long-term measures. And as it said, there were a lot of submissions from a lot of countries about what could be done. These were all open for discussion, and over the time of the meeting, these things were tabled by member states, and some were discussed. Some of the simple low-hanging fruit were things like reducing speed limits to reduce fuel consumption, therefore reducing greenhouse gas emissions. Others were related to the Energy Efficiency Design Index, the Ship Energy Efficiency Management Plan, and so on and so forth. There was no single consensus on the best ones, but there were a lot tabled. As I say, these things will be discussed, debated, and a final list of measures, as I say, cut down to divided into short, medium, and long term, will be in force by the end of 2022. So change is coming. It's been a long time in starting, but it will actually ramp up quite quickly, and it will catch some people unawares. There's no doubt about it. And the reason why they're looking at this, I think you may have heard about this as well, is that the IMO have taken responsibility of reducing global emissions from shipping quite significantly by 2050. It looks at two measures, I guess, by reducing that thing. So looking at the average carbon intensity, so CO2 per transport work, by 40% by 2030, and then another 30% on top of that, 70% by 2050. And to look at the total GHG emissions by half by 2050 based on 2008 baselines. Means there's a lot of work to be done, and it's not going to come out of thin air. It's going to come out from a lot of different ways, and I'll take you through just a few of those quickly. I guess to put it into context as well, what that really means on an aggregate scale. This sort of shows in the heavy blue line is the business as usual scenario starting from 2008. If nothing was done, this is where global greenhouse gases from emissions from shipping would head. The bottom line, the green line, is where the IMO has ambition to get to, and so the question is, there's a big gap. What happens there? And alternative fuels and alternative systems play a big part in that, but it's not just, as I said before, a single solution. There are various ways of doing it. I'll talk about them very briefly, don't need to go onto them, but to break down the emission target or reduction target, they'll be looking at different things. So we're looking at energy efficiency measures, so that's like speed limits, it's like hull coatings, if you like. It's there's a range of optimised maintenance regimes, if you like, as well. Then there's the logistics speeds as well. So that's also about reducing wastage in the supply chain, including port turnaround, berthing, unberthing, and the like. And then there's a big part to play, obviously, in fuel. So if we just looked at the fuel and did nothing else, we would not, as a global community, meet the targets that IMO have set out for itself. So we have to look in different ways. So the future sort of looks at, and this goes a little bit more into this. This is based a little bit on DNVGL research, but it's not unique to us. But these are sort of generally accepted sort of figures, I guess, on where you can find the savings to reach that target. As I said, logistics and digitalisation. Digitalisation in many cases looks at optimising data about your operation, so you can identify wastage and cut that. But as I said, there's greater than 20% can actually be reduced or can be found from that sort of activity. If you look at the hydrodynamics, that's again, the ship design. It covers not only the hull lines but also the propeller, the fins, and whatever else you might have that, including coatings and the like as well. Another further 10 to 15%. Machinery, again optimising systems, 5 to 20, And then the fuels and the energy source, it could be up to 100%. And that's when you go down to zero emission fuels, which by 2050 there will be a little bit on that front being commercially available and viable. But again, I mentioned before that a lot of measures were discussed by the member states at the IMO. Not all of them relate to ship design, but I will highlight a couple of them which came out of some of those areas. So they talk about the EEDI, so the Energy Efficiency Design Index. They're looking at further developing that, taking it up to Tier 4 for new ships. As I say, a lot of speed reduction, speed optimisation and the like. Some of the others ones were research and development into new activities, so that is related to the ship as an ecosystem, not just the structure. Looking at implementing, of course, the uptake of low carbon or zero emission fuels, and that implementation program is along the lines of incentivising through port fee reductions, for example, subsidised fuel, which can happen in places as well, as well as incentivising or encouraging the use of LNG systems, for example, subsidies on some of the systems that go into ships as well. So, range of things which were given some airtime at MEPC. This as well. The Japanese took a slightly different approach, I guess, or a different approach, taking it a little bit more formalised, but making mandatory design efficiency improvements. So not just suggesting these, but actually making them mandatory. That is one way of forcing the issue, and I guess within reason that was reasonably well received, but it's hard to be too dictatorial across all segments and all types. The Danish talked about meeting a certain carbon intensity target which would be set by the IMO. That's one issue that has been raised along amongst a number of carbon states, flag states, that a higher body like the IMO will adopt an accounting method, I guess, to carbon intensity and say, Australia, this is your share of the carbon footprint, this is what you need to reduce, and you go about it any way you want. I don't know, not every country actually was in favour of that, because those which are particularly large flagged fleets like Marshall Islands may not actually have very much influence over what they can actually achieve. But again, these are things for debate. So what is the pathway? I think everyone is hoping for a silver bullet, and I think everyone in this room would know that that doesn't exist. We need to take a measured approach. We also need to be practical about the implementation and the uptake. So when we look at now, next, and the future, now is today, next would be the next 10 years, the future would be heading out towards 2050. And I think these are some of the paths or the options that could be used today and in the future, which we anticipate to start to head in that direction, to get down to that emission reduction target. So the obvious ones are LNG and LPG. We'll talk a little bit more about that at the moment. Over the next 10 years, we're going to see greater uptake in ammonia, in biogas, in hybrid technologies, hydrogen drop-in fuel cells and the like. And then when we go out to the future, when we talk synthetic fuels, we really mean by that, zero emission fuels, but also ammonia as well, where the only byproducts are hydrogen and sorry, what was the other one? And nitrogen as well. But then underlying all of that, you can't just build it and hope that the effect is there. This is where the attention to the management of the ship as an asset and in operation as well as in design will actually come into play. So if we go back to what the Japanese delegation had proposed, some mandatory design guidance may also come into play with these things as well. Focusing a little bit more on the now, and I think that's what we're talking about with what Adam will cover as well. What are some of the things which we're seeing today in this alternative fuels sector? And LNG is one of those areas. LNG has been big and viable and growing in Northern Europe for some time. It's getting more attention in Australia than ever before, simply because we make and export most of it, more of it than any other nation on the earth. So what is the uptake of LNG as a marine fuel looking like at the moment? Short answer is it's going pretty slow, but it's getting more and more momentum as we go along. I think This is just an overview of the sites, the locations globally where LNG fueled ships, and we're not talking about LNG carriers, we're talking about cargo vessels, passenger ships, tugs, or whatever it might be. And you can see a real focus, a real concentration up in Norway and around the Baltics as well. Obviously, with an emission control area in the Baltic Sea, that actually incentivises, I guess, LNG as a fuel in that part of the world, but also most of Europe being an ECA as well. But you will notice that in Australia there are a couple of locations on this map, and this was from AIS data, so this is actual ship data. This is where a couple of vessels who have dual fuel systems are operating. They're in Australia as we speak. So up on the northwest shelf, I guess, and also down in Bass Strait as well. So but also key to this, I think, is which is always surprising, is how little there is in Southeast Asia and Asia in general. It is turning into, in many ways, the hub of, if it's not already, the hub of global maritime business, certainly shipbuilding. But there's very little uptake as yet in LNG, despite the fact that a hell of a lot of LNG from Australian gas field goes to China, Japan, Korea, Taiwan. So we're a little bit out of sync with certainly with Europe and Norway, but maybe that's because we don't have $1 trillion in a global fund like Norway does to actually incentivise the uptake of green shipping in that respect. But it's a bit of a chicken and egg with LNG. Ships won't get ordered with LNG systems unless they can guarantee supply. Suppliers won't supply it unless they can get a certain volume, and in between all of that is the infrastructure to deliver it. So who goes first? Someone's got to take the punt and get going, and that's a little bit along the lines of the program of incentives to try and encourage greener fuels and greener shipping. There are a couple of LNG bunkering infrastructures solutions in Australia, in Melbourne, Fremantle and up in Port Hedland as well, but they're generally quite small because there's a very, very low demand. Put it into context, at the moment there are 354 confirmed LNG fueled ships globally, sailing, 141 which are LNG ready, which were deliberately built to retrofit up to that. It's not a lot when you think of how many ships there are sailing globally, but it is increasing. This last month, I think there was another 17 or 20 new LNG fueled ships on the order book, and that's significantly more than in July and more so. So it is ramping up. By segment, we're looking at car and passenger ferries, the tallest one. This is largely driven by the likes of Carnival and Royal Caribbean, who tend to, because there is an emission control area in Europe and in North America, this is one aspect, one alternative that they can take as well. The other big ones were container ships and what's the, I can't even read that, cruise ships as well. So it's in that sort of space, but there's not a lot in bulk shipping for sure, despite efforts by BHP to lift that number. Those orders haven't been placed, so this is only ordered or known orders, but it is moving in that right direction. Scrubbers I'll touch very briefly along, only to give it in a contrast, because as I said, going forward for compliance after 2020, you have to have used low sulfur fuel or gas oil, LNG or something similar, or have a scrubber fitted so you can use HFO. There has been an explosion in the fitting of scrubbers to ships globally. They're everywhere. There will be more of them, but there is a constraint on the number of ships that can be fitted in time, and particularly over the next couple of years, to expand this number exponentially. In terms of the payback on scrubbers, when the difference between low sulfur fuel, the new compliant fuel, and HFO is very wide, payback is obviously very short. But what we're seeing at the moment is, even in the last 3 months, the delta between low sulfur fuel or gas oil and heavy fuel oil is actually getting narrower and narrower, which means the business case to install a scrubber is getting weaker and weaker by the time. Most vessels, which you see here, have been installed as retrofits. New builds are now getting built with scrubbers on board, but again, that position is starting to weaken because there is another problem with actually getting supplies of HFO after 2020, when very few ships will actually be able to use it. Bulk carriers are the ones which are chief in that, and I guess for Australia in the and the iron ore trade and the like, that's obviously very relevant. About 62%, I think, of all ship traffic around Australia last year was bulk shipping. So it will have a significant effect on Australia, which means that they need to still have sufficient supply for the top up or distress bunkering that happens in Australia. Open loop, closed loop, hybrid scrubbers, it's an environmental issue or it's an environmental furphy, depending on who you talk to. But there are various regulations around discharge of the sulphur from an open loop scrubber directly into seawater, particularly around sensitive areas like the Great Barrier Reef or in certain ports as well. Getting close to the end here. Batteries is something which Adam will go particularly into, but it is again something which is, you can see in Norway. These are ships which actually have systems, diesel electric systems, generally speaking. There'd be some pure electric systems in there, but a lot of them are diesel electric. Again, you look at where they're most clustered, and that's Norway. And that's directly as a result of the incentive program that the Norwegian government have actually initiated more recently. But there are a few in Australia as well. There are several tugs which Svitzer own and operate, which around Gorgon and some of the other facilities as well. So there is a bit of an uptake, but they're limited by their range as well. Batteries don't yet have a solution, a viable solution, to be scaled up to deep sea and international shipping. Interestingly, there are 369 ships confirmed with battery today, which is very similar to the number of LNG confirmed ships as well. So they're tracking similarly, but they have a vastly different sort of way to go, I guess, in terms of their application. And you can see car and passenger ferries. That is that is largely driven by the short ferry rides between the fjords and around the coasts in Norway as well. So they've been the real powerhouse in doing that sort of taking that initiative forward. So again, without wanting to ring alarm bells, but rather than setting the scene, is that things have been moving very quickly over the last 18 months, I guess, as IMO 2020 comes on. People are looking for solutions to avoid the price hit that will come from having to go to marine gas oil or low sulphur fuel. But these are not the only things that the shipping industry needs to be worried about, because when you sort out sulphur, you then have NOx, and then you may have noise and vibration, and you have particulate matter. There's a whole range of things which are on the community's agenda to try and fix. We talk about the biofouling as well, and the invasive species as well. That's something which is getting increasingly focused in this day and age. As it's mentioned there, underwater noise is a very key one, and there's also ship airborne noise as well. So one of the biggest problems that Gore Bay has here, the Shell or the Viva refinery or Viva facility there, is not so much with emissions, because they're running on gas oil when they're in harbour, but it's the airborne noise, not only at the high frequency but the very low frequencies as well, which actually then can propagate right across to Balmain, and I don't know the full effect, but apparently it makes you feel very sick. So these are things which are on the horizon. Ship recycling, we were talking about that a little bit before. That's another big issue. We have a class notation around that, and then also the plastics from ships as well. We've all seen the news and the YouTube clips about those things as well. So there will be, on the back of all these new issues, or not new issues, but things which are coming into the spotlight, increasing attention to regulations. And it's not just one size fits all, even in a country like Australia. There is the national regulations, there's the state regulations, there's the port regulations, and that includes the EPA, which don't traditionally work on water, but because the port facilities are subject to EPA regulations, there's a lot of attention in this area as well. So it's not to prepare for the storm, but it is a little bit about being ready for change. I think as we go, just about to finish here, and I'm sorry for dragging it on too long, but the changes that are being talked about here will start to impact vessel design and operation very soon. We, as a company, and certainly from the advisory side that we do a lot of work in new vessel design, assessing them relative to regulations, doing model testing around emissions and around those things as well, and about efficiencies as well. There is this push from the supply chain, from the charterers, if you like, to make sure that shipping is actually using as low carbon fuels as possible. They're looking at carbon neutral fuels as well as something which needs to grow in recognition, but also in application. We're looking at these things they're not going to be announced tomorrow, but there's a lot of talk about this, and it's an ongoing process. And believe me, I'm sure that we'd all experience it by the time that a new regulation about carbon emissions or zero emission fuels comes in. There'll be a lot of people who said they'd never heard about this before. But we've been talking about this for 20 years, and it will go on as we get closer to 2050 as well. So I'll take a breath now, and I'll get out of your face. It was to try and set the scene, not to ring alarm bells, but it was trying to set the scene that what Adam and the design team and what DNVGL do is we're trying to service the industry in any way, shape or form that suits the purpose. And that means looking at different ways of applying technologies, looking at research into alternative fuels, and also looking at ways to actually make sure that whatever the changes are is practical and as feasible as possible, because there's still stories out there, still prototypes and hybrids out there about wind sails for international shipping. Really good in theory, but is it really going to work in practice? So we're always at the forefront of testing these things and getting out and doing this. And I'll hand over to Adam now, who takes a little bit more technical view than I will, but happy to take questions later if need be, but thank you.
Great, thanks Jonathan. I think he's pretty much set the scene of what's coming, and I'd dare say that as Jonathan's put forward, he's more sort of like what he's seeing in the IMO, and what I'm doing is more with ship structures and what we're actually seeing through DNV. So by no means am I an expert in some of the technologies I'm talking, but I'm trying to say what we're trying to provide, what we're trying to do, and what we're going to go through. And I will say that a number of the technologies that are coming, by what Jonathan said, we're going to be seeing those in the next few years, whether we like them or not. That's just a synopsis. I'll actually just go through that. Tonight I'm going to talk primarily about three main technologies that are being used in ships: batteries, fuel cells, and gas fuel. Those can all be actually used together or independently. So it's a little bit confusing, and if you see sometimes that items are being repeated, I apologise, but as I say, you quite often can have a gas fuel installation and have batteries, and you've got a hybrid, or you've got fuel cells and batteries to store power. So I'm going to start with batteries. Just briefly, and I'll use this with a couple of the different slides, is looking at the energy densities. In particular, the talk tonight is high-speed light craft, and the reason I chose that one is because Australia, we're a very large producer of the high-speed light craft ferries. We've got a number of builders in Australia, a number of designers, a number of successful designers, and I think we're servicing the world to a very good rate. Looking at this, you can just see that there are a number of different battery technologies. It might not be immediately obvious, but on the vertical, we're talking about how much power it can put out just quickly. Can you have a 100-watt light globe? And then on the horizontal, how long can you keep that 100-watt light globe going? So your lead acids are in the grey, and then you've got your lipos and a number like that. So technology's developing, and a lot of things are happening in the market. I must admit, when I started looking, I wasn't sure of, when somebody said a battery, are we talking, a tank with some acids in it? What are we talking about? So there are actually different formats. You've got obviously the different chemistries, and then you've got the different ways that those are presented, which presents many challenges when it comes to actually installing in a ship. What we're seeing is, it's not one size fits all. There's different ways to handle that. one thing that we need to consider, the way that DNV actually is approaching is how to install those. I'll quickly run through the items that are considered, and basically you need to look at how your batteries are being managed. It's not just as simple as having connect your batteries up all in series or in parallel and then just run with the power. You actually have to monitor every cell. You have to make sure that each cell is being, its state of charge and its state of health is being regulated. When you charge it, you have to actually look after each cell. If you don't do that, you'll find that you've got one dead cell and you're actually creating problems. Ventilation, when things go wrong, you need to be able to get rid of gases. When they fail, they typically what they call gas off, and then that gas off can actually lead to quite corrosive, quite dangerous, quite toxic chemicals. So these are the sorts of things you need to do. Power system integration, you can't just, again, have the batteries and hope everything works. You need to actually see how that's working with hotel load, working with your engine requirements, working with various different systems that are on the shore. Fire protection. We've all heard about people not being able to carry their laptops or their phones in certain places. Well, it's very similar on ships. You need to basically be able to manage that, and if things do go wrong, what do you do about it? Thermal management. When you've charged your battery on your phone, you've probably felt that it gets quite hot. Again, there is a lot of heat, both in its use. If you're actually demanding a large amount of power from a battery, you'll find that that can actually create a substantial amount of heat, so you have to cool them. And if you don't cool them efficiently and effectively, they can actually then break down and you have a failure. And then the last one, inversion technology. Now, one thing I'll actually note is that with electrics and batteries and the like, one advantage of that is you can actually have your power source, your batteries, almost anywhere on the ship because you can connect it via cables, and you're in a situation where you can actually optimise the location throughout the vessel, which is something that I think will be beneficial for high-speed light craft. Now, I mentioned the fires. This was a demonstration done by DNV Kima, and they wanted to actually look at what happens to a battery. I believe that it actually pierces the side of the cell. You can see that it's gassing off, and then it obviously catches fire. Because you think about the amount of power that's stored within a battery. This is a cell, a pouch cell, and once it goes and once it actually shorts, there's no controlling it. Very difficult to manage. I mentioned that the vessels, there's no one single source, and I think the next two vessels I'm about to show you are a good example of that. The first one's the vision of the fjords. As Jonathan mentioned, that the Norwegians are really pushing ahead. So one of the vessels they've got, or one of the companies they've got, works near Flom, and it's a I think it's actually a carbon fibre vessel, 42 metres long, and this one's a hybrid with batteries and also it's diesel, diesel. Quite an interesting design, quite unique. The thing is, its sister ship, it looks very much the same, but in this case, it's full batteries. So they've limited, they've learned from the technology of the hybrid, and they've gone to the batteries. Now, one challenge that was put forward to having a vessel that requires that much power is how do you charge it? You plug it in overnight, you know? Well, because of the requirements, they actually worked out that they could do what's here. So this item here. They've called that the power dock. And that's got 5.5 tonnes of batteries in it, and it'll sit there and it'll literally trickle charge from the local grid during the day. And as the vessel, the Future of Fjords, pulls up, it's able to be charged within 20 minutes and keep going on its run. So yeah, pretty amazing thing. So this is when looking at the installation and the way forward, and DNV is what we're working with, and DNVGL is actually originally Norwegian. So it's quite obvious that we'd be working with it. So we've got notations within our rules. In particular, they are actually in the rules for ships. However, if you're doing high-speed light craft, you start with the rules for ships. You talk to us, and we make them fit. So that's not too much of an issue. There's not much point actually writing two separate sets of rules because the basics of safety, etc., are pretty much the same. The notations we've got is battery, battery with a notation of power or safety. The power one is when the vessel is basically using battery 100%. There's no second source of power, whereas safety is where you've got a hybrid. Second one that I hope to talk about is fuel cells. This is a vessel that DNVGL is working, we're working to certify the hydrogen system and the propulsion system. It's an interesting design. This one's actually not commercial as such. It's a yacht. The idea will be that the designer, Swiss Sustainable Yachts, are putting forward a design to pretty much take advantage of lots of wealthy people who would like to have something that's green. So, what's not obvious in that picture is the top of the sun deck is actually a solar panel. So it's actually able to charge some of its own. Sorry, I can't read my notes because of the way we've got the recording set up, so I can't read some of the notes. But basically, the solar panel on top will help recharge the batteries, and therefore will actually extend its operational capabilities. And DNVGL's working with the certification of the hydrogen systems. This, I think Jonathan mentioned that there were some ideas with wind. This vessel's actually in service. I think if you go to the website, the Race for Water, they're very much about the plastic pollution within the world. And that vessel is going around, I think it's in Asia, I believe. I think it may even be in Singapore. And it's got solar panels, it's got hydrogen, and it runs around. But what's interesting about it is its maximum speed's 9 knots. So that shows you some of the limitations you actually see with wind power, with a kite, with solar and with hydrogen, is that when you've got long distances you then had to manage what power you've got available, and therefore your speed comes at a price, you lose your speed. So,
did you say that one had fuel cells as well?
I believe so, yes.
Yeah, okay.
Yep. 200 kilograms of hydrogen stored in 25 bottles at 350 bar, and then it uses fuel cell. As I mentioned with the batteries about energy density, hydrogen, as you can see from the graph, has the highest energy density available. The only problem with that is you then have to store it. Hydrogen, as we know, is quite a challenge to store. You've either got a high compression, and that usually involves low temperatures. So it's very much a challenge. The other gases are there as well. They also present similar challenges. Mentioning fuel cells, I must admit I was a bit unsure of what fuel cell technology there was. The picture on the right actually is different chemistries. It's not one fuel cell using 4 or 5 different chemistries. It's actually a graphic showing the options, and you can see here that there are a number of different chemistries. What's interesting you can see from these is actually the temperature ranges that are run. Some run quite low, 80 to 100 degrees, other at 800 to 1,000 degrees. So running those on a vessel presents safety issues, presents management of that thermal load, so it becomes quite a challenge. However, it does have the benefit, low emission, high efficiency and part load. It's the maintenance and etc. is very different to a diesel. Comparing it with a diesel, and again this is looking at the high-speed light craft or the ferry option. If you look at this is comparing an engine 3,600 to 3,900 kilowatts. A Wärtsilä engine, it's much larger, it's much heavier, and compare that to a fuel cell, and it's smaller, it's lighter, and you can actually place it where you want. It doesn't necessarily need to be right adjacent to the propulsion system. So there you go, there's a benefit, there's something that we can make use of, but does it have the energy density required to get you the distances or the speeds that are traditionally seen? Just quickly, there are a number of graphs, and I know that graphs can sometimes be a little dull. I mentioned some of the challenges. If you look at the likes of hydrogen, it's in standard temperature pressure, although it's 20 degrees. You're talking about it's got a very low density, so that means you've got to do something to store it. You've literally got to compress it, and you've got to keep it. Methane's there actually compared with natural gas is the reason that one's there. Next one, diffusion. Again, when we're thinking about safety, hydrogen moves faster than helium through air, and basically it becomes very explosive very quickly. So that's something that needs to be thought about and considered. And it can even diffuse into metals. Mechanism can lead to hydrogen embrittlement. So it's not just a simple matter of I've got a hydrogen tank and I can disregard everything else. I need to think about what other parts of the vessel I need to modify. Energy content. Well, as I mentioned before, hydrogen, it's got the highest energy content per kilogram, but you've got to get it in those kilograms that are manageable and usable so that you can take advantage of that. Flammability. Now this one's talking about safety. Hydrogen is from 4% to 75%, which literally means that it doesn't matter how much is released or whether it's a lot or a little, whether it be a small space or a large space, you've got something that needs to be managed. It's something that can become very dangerous very quickly. Compare that to methane's propane and traditional petrol, and you can see that that presents a challenge. Ignition temperature, again, it doesn't take much. Doesn't take much to set fire. So the other thing that's quite interesting is that a hydrogen flame is invisible. So it's not immediately apparent when you enter a space that's got a fire or the like. I mean, assuming you haven't had an explosion. But if you've got a problem, it's not immediately apparent. You can't see it. So looking at regulation and the way that hydrogen is managed, you might be familiar with, and I think one of the next slides is, it talks about the IGF. We need to look at the way that hydrogen is considered and installed on a ship. So you need to do that by an alternative design approach. There are guidelines for those alternative approach, and I'm just giving a reference to the IMO document. So we're talking about safety, reliability, dependability of the system, and it's got to be equivalent when compared to a conventional system. That sets a huge challenge. To say that it has to be as safe as a diesel engine, where you can turn it off, you can literally isolate the fuel, and everything's fine. That's certainly when you've got a gas which can move differently, you've got different systems, fuel cells, it can be quite a challenge. However, we're seeing that things are coming, and I think, you know, literally I looked at some research, it was like a year old and it was already out of date. Things are happening very quickly. This is a vessel that's one of our local designers, Incat Crowther, has been working with Californian government. As Jonathan mentioned, with many of the vessels being in Norway, the impetus of that has literally been sponsorship, has been grants, has been operations from governments and the like. So you've got a situation here where the Californian Climate Investment has come up with a ferry that runs on hydrogen. What I found interesting in this vessel, and this one's called Water Go Round, which is you won't forget that one quickly. You can see that the hydrogen tanks are actually stored on the upper deck. Now that's got an advantage in the fact that you've now got a ventilation system. It looks at the gases can be ventilated to atmosphere, and you don't have the passengers immediately adjacent to that. However, you lose passenger space. So that was a decision that was made to take advantage of one, but you lost another. I mean, it can still carry 200, how many passengers was this one? This one will actually be launched later this year, as I understand. I don't have the number of people. Oh, is it there, is it? Yeah. Okay, sorry, 84 passengers. Okay. So that one's, as I said, designed by Incat Crowther, which are in Sydney. So as I mentioned before, the IGF code, that came into force 2017, and it's mandatory for all ships using gas. Now, one that always comes up, is it IGF or IGC? IGC is the carrying of the LNG, etc. So that's more when you're talking about a crude carrier, if you like, or a gas carrier. So now it's interesting that the IGF code currently looks at methanol, low flashpoint diesel, other fuel systems, but doesn't include hydrogen. You have to do that by an alternate design. So there's no intention, as I understand it, to revise that to include the hydrogen. Regarding the DNVGL rules, again, it's rules for ships, part 6, chapter 2 is where you'll find all the reference for where I'm working with today. Fuel cell notations there, it exists, and it goes through basically the safety, the locations, and the systems that are required. And again, we've got notations very similar to the battery. FC stands for fuel cell, and power when it's 100%, or safety when it's used in a hybrid system. gas as a fuel. In this case, we've got the approach that the rules have taken, and that is we need to separate the gas separate the gas from points of ignition, keeping obviously mechanical damage, etc. So I'll talk about more of that in the next few slides. You've also got leakage, so you've got to basically double wall tanks, double wall piping. Leakage detection, so if you do have a leak, then how do you deal with it? Where do you have a venting system? Do you have what alarms, what processes are taken? And then you've got isolation of the leakages. Now, as I mentioned, protecting the tanks, these are large LNG tanks, and the IGF code requires that they have to be a certain distance in from the side of the vessel. This is to obviously account for collisions, and the number that's normally put around is the breadth of the vessel on 5 or 11.5 metres, which is ever less. That's from the side of the vessel. You've also got the rest of the vessel, which is typically B on 10, and in no case 0.8. And then on the lower surfaces of the vessel, B15, B on 15 or 2 metres. And that's also applicable to high-speed light craft, but it becomes a bit more of a challenge when you've got multi-hulls, but that usually gets dealt with on a case-by-case basis, depending on the arrangement of the vessel, the likelihood of damage protruding through the hull, and a trimaran, the side hulls may be actually quite small, so therefore you've got a different situation. The picture there is actually the tanks being put in the Francesco, which is Incat Hobart vessel. They are a double wall tank. They're a Type C, and quite a challenge actually when you putting those in. It's not just a simple matter of I ring up and order a tank. The tanks are quite they're purpose built. They're specific for the vessel. They've got many challenges. Again, unfortunately, I can't read my notes. But what they need to be designed for is they've got ultimate design conditions where you need to look at dynamic loads, whether that be motions of the vessel. So you've got sort of yield loads, etc. for the mounts. You've got pressure loads, internal, external loads. You've got thermal loads, sloshing loads. So they're your normal loads. You then have to look very carefully at fatigue. Because we've got a vessel that's moving through a seaway, constant loads, and this is quite a sensitive piece of equipment, you look at fatigue. So you've got your mounts, which need to be considered, and you've obviously got temperature effects on those mounts. So that becomes quite a challenge for that. And the last one is collision loading, collision and fire loading. So it's, as I say, it's not just a simple matter of just putting a good old tank in. It's quite significant. Next slide. I think, as I mentioned before, Type C. Now these are the tanks that you just saw an image of, and they are the ones that are double walled. They're inherently protected. But what we're seeing is we're seeing other tanks that are potentially going to come forward, but those ones will have to have their safety considered, and probabilities of damage and dealing with failures, etc. will have to be dealt with. I also mentioned safety of the machinery space. There are two types of engine rooms. One is gas safe, where you've got double wall pipes, and it removes the possibility of gas leakage from the engine room. As you'll see there, pretty much gas comes in, protected, into the engine, and the rest of the machinery space is your typical machinery. The other one is what they call an emergency shutdown. Now in this situation, the pipes are not double walled. Instead they come in, but the way you mitigate the safety in that case is you high monitoring, and you've got leakage detection, you've got ventilation requirements. So you literally, it's a different approach. You're assuming that you might get a leak. One thing of note is when you've got a shutdown requirement from the explosive safety design, you need to have independent propulsion systems. They must be divided to 2 or more engine rooms independent of each other. Emergency shutdown, sorry.
Emergency shutdown.
Sorry, I may have said the wrong thing. Emergency shutdown. The bunkering process, it's different to your normal heavy fuel and diesel fuel alike. You've actually got to prepare if there's the cooling, inerting of the system, connecting, draining. There's obviously the temperature effects. There's a lot of training involved, so it's something that needs to be considered. There has been other systems put forward where you've got a what do they call it? Where you drive in and you actually load a cell on, and so the idea is that it'll be a pod that's loaded onto the ship and then taken off, and that removes the requirement of the bunkering. Each approach has been put forward. This one's being used on the larger vessels. High-speed light craft is happening with the Francesco. So you've got ventilation. You've got to have systems in place to look after it and manage. As I mentioned, this is Francisco. This was a vessel launched 2013. This is from Incat in Hobart. It's dual fuel, so it's got gas turbine capable of running on liquid natural gas or diesel. A little animation. What's interesting at that is when it runs the gas turbine at the light ship trial speed, it achieved 58 knots. So that's an awful lot of power going through, and that's using the LNG. So that's seriously impressive power. Of interest, the Francisco, Incat have delivered more vessels and have got orders for more. So they obviously consider that to be quite a good process. Again, referring to the gases, which is the IGF code, it's mandatory for the gas, and it's got detailed requirements for liquid natural gas and compressed natural gas. Again, we're looking at Part 6, Chapter 2, where we've got the 3 different options. We've got gas fueled for liquid natural gas, we've got low flash point, and other gas fueled as well for liquid petroleum gas. So there's, as you can see from the number of pages and the contents, it's quite a large section required. So that's in a nutshell where we are with high-speed light craft and then the future fuels. So I hope that's been interesting, and if there are any questions.
We certainly have time for some questions, so who'd like to pose the first one? Down the back. Yes.
So, with bunkering of the LNG, obviously when you bunker fuel oil, you do a lot of testing to ensure it's of the right quality. What tests go on with LNG to ensure that it's of adequate quality?
Not sure. So
You take a bomb and you get it tested for its energy quality.
okay. So
Called a bomb.
right. It sounds like there is testing called a bomb. Sorry, I'm not an expert in some of those. I apologise. So.
I was just very curious.
They're developing standards at the moment, so it's over to Alan.
Yeah.
Alan Taylor, I'm member of the Institute of Marine Engineering Science and Technology and Naval Architects. You put on the board there again the nitrogen. I said to a treasurer in Australia, I can't see trees up there, because that's what, sorry, not nitrogen, carbon. It's the oxides of carbon, the oxides of sulphur, volatile organic compounds. And you go out and you talk to the people in society and they say all the carbon emissions. And we don't even get it right in the industry, but we know what they are.
True. It's typically greenhouse gases are where the concern is.
Yeah, but the problem is they don't come out and say greenhouse gases, they say carbon.
They do. Yeah, and we've had a Prime Minister that said you couldn't see it, so you couldn't measure it. So we've got issues to tackle.
Well, I told the treasurer here one time in the meeting in Sydney, I said, I can't see any trees up there. I looked around, plant trees. Jeff. Oh, sorry.
Hi, Joe Goodwin. I'm RS. I've got a whole raft of questions here, so I won't try and ask them all up front. The first thing was you, Jonathan, talked about the industry reducing its greenhouse gas emissions by up to 70%, I think, in the long term. Are we talking here the industry total emissions, or are we talking emissions per cargo tonne mile or something? Because surely that will be more relevant. I mean, you can always reduce our emissions from the industry if we shift more stuff to air freight, but that's not going to help the greenhouse gas emissions very much.
I think I showed that there's the the emissions density. So that's emissions per cargo tonne mile, and the other one is total emissions. So that's the total greenhouse gas. So 50% by total and 70% by density. Yeah, so they are trying to do that, but that's an aggregate global fill, and that's when we talked about there've been some submissions to IMO about this so-called accounting method, where they'll say how many ships does Australia have? Okay, that's your budget. You need to reduce it by 70, and if everyone does that, then we meet the target.
Okay, thank you.
Yeah.
Second question, but I won't try to do well. I'll pass this over to one more question. With my chemistry is a bit limited, but one of the key things we've done in recent years is to reduce the sulphur in our road fuels, shipping fuels. I presume that sulphur is still coming out of the ground in the crude. Where does the remaining sulphur go? And as transport users, do we just think that's not our problem?
As I said under my breath, my chemistry is worse than yours, I'm sure. But I do know that is one of the issues about and that's with the scrubbing. When you've got exhaust gas scrubbers where they're taking the sulphur out of the exhaust gas, one of the biggest problems is where to discharge that to. So this is the problem with open loop and closed loop and hybrid scrubbers. And there is a lot of misinformation or disinformation or lack of information about the actual effects of that sulphur into the environment, and I won't go there. But it's also one of the issues, again, I think Alan, talked about the community grabs onto something and sort of goes with it without actually knowing the science or the effect of it. And one of those issues is around discharge of sulphur into ports. Some ports won't accept sulphur discharge, so therefore you have to carry it and you have to take it somewhere else. And it's like moving the problem from one point to another. It's still a problem, and that's, I guess, why, as I said, SOx is the cause of the day. NOx will be also there, VOC, particulate matter, all those things will come as well. So once you fix one thing, you'll move on to the next thing. I think there's no issue about that. And that's why zero emission fuels is on the way, and it's also why a lot of companies are now, and BHP has just been putting this out into the press a lot, is they're looking at Scope 3 emissions as well and Scope 2 emissions. So these are the emissions which are created in the generation of energy which are used on the ships and stuff like that. So you can't hide it up in the Hunter Valley because it's going to come down. It needs to be accounted for. Yeah.
But they're also saying now that BHP is looking at the end users of their products that they produce. Absolutely. For them to reduce their oxides of carbon, etc.
And when I talked about the influences on a lot of these things, they're not necessarily technical. They're going to be the communities. They're the people who buy the goods in Kmart. They're the ones who are saying to the suppliers, what are you doing about reducing greenhouse gas emissions? And it's a long way from bunkering a ship at Port Botany, but it will affect it at one way or another, yeah.
And back? Yep.
I know all the rules, regulations and aspirations. What about the enforcement? How is all this going to be controlled? I mean, people aren't going to do this willingly.
The way it was once described to me, that people in the shipping industry want to be, or the best operators want to be the first of the last to move. So they want to wait until it's absolutely necessary to do it. So you're right, they won't do it unless they have to, quite often. But there is, port state control, Tokyo MOU, they have regimes which actually target, they have white lists and grey lists and black lists of ships. So there is some data, and this is where we talked about digitalisation and the use of big data, is that they'll be able to target ship types, ship systems, owners, operators, trading patterns and stuff by looking at where they're bunkering, where they're going to next and things like that. So there's ways to sort of target people, but I I think, as we said with AMSA, AMSA don't have enough surveyors who can go, or inspectors to go on board every ship and check every bunker line and every tank. So they've got to look at some way of actually prioritising. You're absolutely right. Enforcement is the key. There's no point in having a rule unless it's enforced.
So ultimately, it comes down to port state control.
I'm not an expert in that. It is, yeah. And flag, yeah.
Yeah, that's the one. You're next, Greg.
I was dealing with Aquis at one stage and they wanted evidential breatharisers, and I said, you put one of those on the ship, they can have it apart in 5 minutes, fix it up, it'll be perfect when you read it. But just as an example, and what you were talking about before of reducing fuel consumption per tonne mile, in 1978 I took delivery of a 108,000 tonne bulker that burnt 75 tonnes of fuel a day. 1980 I designed the ships and took it into account, and I took them up to 147,000 tonnes and could run 70 tonnes a day. And the last big bulk carrier was 232,000 tonnes. It would run at the same speed, and I got it down to 60 tonnes a day. And that was taking a design point into effect of the hull, the coatings, the engine, etc., to get the maximum efficiency out of the ship. And that was back in 1982.
Yeah, I mean, I think as the slide that I showed, that there's a lot of ways to reach the target, and design is a key one. Operation, attention to detail, looking at the whole system. As I say, it's an ecosystem that you're dealing with. It's not just one or the other. And I've done energy efficiency projects for a whole range of different segments globally, and believe me, one of the quickest and easiest ways to reduce fuel consumption is by actually having it as a KPI and putting some attention to it. The fact that there was a project on energy efficiency meant all the superintendents knew that the boss was looking at it, so they started to operate a little bit more efficiently. And overnight you almost get a 2 to 5% efficiency gain. But it's not one thing, it's many things connected. And the digitalisation of shipping and systems is enabling a closer control of all those different and disparate data sources, so you can actually make informed decisions. I think that's the main thing. And design is a really great way to start.
To put that in perspective, some of the emissions, one of the statistics I was reading was greenhouse gases from the shipping industry. If it was a country, it's 2 to 3% of the global emissions, and that's bigger than Germany. So, when you put it in perspective, reducing it by 50% is quite significant.
Yeah. Jonathan, when you're answering, can you just stand a bit closer to the mic?
I can. Sorry, I didn't want to crowd.
What percentage of the methane gets vented from the LNG on ships?
Sorry, I'm not an expert, can't advise on that one.
It's good going to move to gas because it burns more cleanly in terms of reducing carbon intensity relative to other fuels. But you've got, if you're venting the methane off even small amounts, that's extremely potent greenhouse gas. So that has to be weighed up too.
Yeah.
Is that something quickly on that? Sure. I can just say something quickly about Woodside. So Woodside have been operating their OSV up in the northwest. And they're obviously very mindful of methane, slip and methane emissions based on their LNG experience and also the shipping. So they're very upbeat about limiting methane slip. They've got numbers, they've just produced a very nice report, which I think says you get a 25% reduction. Theoretically, that's the maximum you can get. They're saying they can get about 20% reduction, so maybe we can count 5% for the methane slip. So it's a bit, but it's not excessive.
Any more questions? Yes, down the back.
So we alluded to it earlier about wind power, and obviously I get the sense that there's a very big scare about using wind. Obviously there's been kites, there's been sail-type devices and stuff tested, trialled, as very much prototypes. And while not perfect, they have presented some pretty good findings. Why is there such a scared sort of, why are we chasing basically a few percent savings with fuels when the entire maritime industry survived for about 3 millennia wind power?
It's a good question, and it's one that's definitely been knocked about. I know in our office, when we see these new vessels, we just say, well, hang on, you can go faster if you put a sail up. I think what it comes down to is reliability of transportation. You've got wind that can come and can go. You've got a situation where wind can be in the doldrums, nothing, or you can be in a extreme weather condition. That's what I was about to say. So you're in a situation where, yes, what it's being used at is it's being used as a supplement. So as you saw in the not water go round, it was the other vessel, and they're using it to supplement their other power. And it's apparently that kite system is fully autonomous. They just literally, out they go, and once they work out there's a wind speed, it goes up and it manages itself. So it's happening. I don't think there's necessarily a fear. I think it's more just a matter of, like, that's only one part of the solution.
Yeah, the kites, the flat narrators, all the systems.
Definitely.
Most of them cut between 30 and 60, even up to 90% of fuel consumption, because once you get out in the open ocean, the winds are pretty strong.
Yeah, I mean, that one that I had the picture of, they said even with the wind, maximum speed 9 knots. So perhaps they need a bigger one. I'm not sure. So, but yeah, very good point.
Robert McMahon, marine engineer. There's talk about LNG terminals in the Pilbara, but Australia's a big exporter of minerals, iron ore, coal, LNG, and there's talk around of home-porting ships in the Pilbara that can bunker LNG for the Asian bulk trade. And there's LNG ships starting to operate in Bass Strait. So I think Australia might have a bigger future in LNG in particular, but in all of the technologies, where are the ship's crews coming from for the future? Because older engineers are not trained in the new technologies, so there's got to be a new generation of young engineers in all these different technologies. Where are they coming from to man all these ships that are coming on stream?
I am not an academic, but I do know that one flow-on effect from the continuous shipbuilding program, the naval shipbuilding program, is that several more universities than they were maybe 5 or 10 years ago are now looking at engineering, marine engineering and technology around that. And with that, I mean, Navy and Defence is at a different level of sophistication, but you're getting more people training in engineering, which can be applied to shipbuilding and ship operations. I mean, that's just Australia, but where it goes globally, isn't that the biggest problem we all have in terms of getting young people into meaningful academic careers?
Be an avenue here for the Australian Maritime College.
Yeah, exactly. So I think you're right. Absolutely, there'll be new requirements, I guess, for training and experience. And you know, I struggle myself with my new iPhone, which I got. I thought I was comfortable with my old iPhone, but now I'm struggling with the new one. So God knows how it's going to go in the future. So I think I'm no different. I don't think there's any silver bullet on that one. It's about having more places teaching the same, teaching the new stuff, I guess, as much as anything. I think Australia's well placed.
Thank you. One for Adam, I think. You showed a comparison of a diesel generator alongside a fuel cell system, but you didn't include the fuel storage. When we looked at the potentially fuel cells for submarines, the biggest problem was that the hydrogen storage was most efficiently done in hydrides,
Yes.
and they were very heavy. So your little boat there that had 284 kilograms, I think, of hydrogen tanks. What would the equivalent energy storage in diesel tanks?
I can't give you exact numbers. But I
Because I think that may be overwhelming in the
Yes.
other direction.
Yes. Listen, I mentioned that I couldn't see my notes. One of my notes was for that vessel was that, that comparison, is that you've saved this space when it comes to your engine room, and you've saved the space and the simplicity, and you can have that, your fuel cell, you can put it in the, you know, obviously after the forward conclusion bulkhead, you can place it wherever you want, but what you've saved there, you now lose in the storage of your gas. And then you've got your systems to protect that tank. I mean, as you saw with the installation of the LNG tank, where it had to be BN5 from the side of the vessel, that compartment actually can only have that tank in it, nothing else in it. You've then got a gas preparation tank, a void. You've got other areas where it becomes something where you've got to manage the pipe work. The pipe work has to be segregated. There are a number of things that are a challenge. These challenges are obviously going to be met, and you saw with Water Go Round, they put the tanks up on the top deck. That was their way of dealing with it. Obviously, stability is not an issue where the vessel's operating. We're talking about San Francisco Bay. So it was a way that they that balanced the approach. I agree. Yes, if it was a submersible, it's a challenge.
Another of the safety aspects you mentioned. Can I have one more? Is that
Last one.
you mentioned for the gas fuel, I think the hydrogen fuel, that the fuel pipes were double walled.
Yes.
Now, on all our diesel engines for many years now, all the high pressure systems have been double walled. I've still seen actual vessels where a leak in the high pressure system that was all supposedly double walled has filled the engine room with a fog of fuel, and I don't know why it didn't go up. And so that kind of safety system still has its limitation. That was just a comment, really, because.
Listen, I appreciate that every system will have its, Swiss cheese. It'll have its hole in the potential for things to go wrong. Whilst I can't make direct comparisons between the high pressure fuel line and the gas fuel lines and the double wall, I would hope that, in fact, more than hope, the double wall actually should have monitoring systems within it. So if the internals fail, then that should actually be picked up and actually monitored. So it's not a direct, hopefully, I'm not sure if the diesel ones would have the monitoring of the gas within the wall, but hopefully that they've actually addressed those concerns, looked at thicknesses of materials and material types to reduce that. But yes, you're quite correct. Every system has a limitation.
Yeah. The example I was quoting, in fact, the double wall system was designed to monitor any leaks from the high pressure system, but
Yes.
the leak came from close to where the pump joined the double wall system. So.
Right. Okay.
It's half a question and half a comment. In the design of the North West Shelf LNG ships, we were able to get a design index from what I got the savings for in bulk carriers, because we dealt with the insulation, and we took enough heat in from the insulation to boil off the gas to power the engine. And if we needed more, we then used our bulk system, which is the LNG generating system, to top it up. And the base criteria there was to deliver the maximum amount of fuel to Japan to get the maximum profit for some people in the room who work for those companies. So it's an interesting concept, and I use the same philosophy we developed in BHP in the LNG ships. And just to remind people here, they've now been operating for 30 years. The first one, the North West Handling.
Good. Any more, ladies and gentlemen? Any more down the back? Would you like one last one? Yeah. This is it.
That's all right.
Yep.
One thing you mentioned, it was a new idea to me, was ammonia as a fuel. Obviously that would reduce it would eliminate the oxides of carbon problem, but certainly in vehicles and so on, we have a real problem with oxides of nitrogen. So
I mention it, and that's all I can do. It is something. I actually I met a guy who works for MAN, and they're working on an ammonia fuel two-stroke, which can be scalable to a bulk carrier. They're 3 years at least away from having something that works because of all these issues. One of the biggest problems is the storage and the location. So So I don't know the I don't know the technology deeply enough to be able to say this is how it happens, but I do know it's an area that they're actually working on it. And as I say, DNVGL, MAN, there's a few other companies as well are working on this project with the EU to come up with a viable alternative. And of course, Australia as a nation has a hydrogen strategy, which is looking very deeply at how hydrogen can be the next feedstock for the generation. And this conference in Melbourne only 2 weeks ago was called Ammonia equals Hydrogen 2.0. So they're really taking that down. And interestingly, apart from the odd OEM sort of a speaker, most of them were academics. So it is still largely at academic stage. Certainly, and I talk about what Alan was saying about 30 years for the LNG gas carrier or whatever it is. We're talking about LNG as being a viable transition fuel, I guess, from heavy fuel oil to zero emission or low carbon or low emission fuel. But the transition is not a year or 2 years or 5 years, it's 30 years. It's 30 or 40 years. And I think that's another bit of it that needs to be right-sized within the communities and the business sector's mind, is that you don't suddenly turn it off and find a new alternative tomorrow. You can't change all the ships floating who will be built with LNG to something which is zero emissions overnight. So there is a timeline on that sort of stuff, yeah.
The whole electric car issue, which is not relevant to this talk, but it has the same problem, I think.
Has there been any interest looking long-term, in a few decades' time, in increasing use of nuclear propulsion?
Interesting enough, when it comes to ships, there's actually been a number of nuclear-propelled ships and the like, but literally, sorry?
Not recently.
Certainly not recently.
Apart from
a couple of the
submarines and US submarines, for example.
I thought there was one up in the Arctic, a Russian vessel. Yeah, they do. But I dare say that with a political motivation, it's just, that'd be a very steep wall to climb. Yes, it's there, but it's not being put forward, and I don't think we've got a nuclear notation.
But I think it is,
we can do it.
I would say that it certainly shouldn't be off the table, because it is in that category of zero or very, very low emissions. But it's the safety aspect which is there. But to sort of contrast that is that, there's a lot of talk, there has been a lot of talk about biofuels, using feedstock and, from plantations and the like. But the flip side of that is I heard that over in Brazil, where it's a viable alternative, is they're cutting down the rainforest to grow palms. So that is the palm oil which actually goes into the biofuel. So there's a counter effect to having a biofuel. It's actually reducing the Amazon. All that sort of stuff. So that's why I would say it's never off the table. But I think, as Adam says, the chief thing is public perception and safety, and until it can be proven to be safe and can be operated in close proximity to human beings, I think it's probably going to be too hot to touch. My guess is anyway.
I think.
Just one more.
Talking about ammonia as a fuel, but I know ammonia as a refrigerant, and ammonia turbines are much more efficient than steam turbines, and low temperature heat can be used to recycle the ammonia. So, and I believe there's plants being built in Russia with this technology. Is DNV looking at any of that technology at all?
I think, as I mentioned before, that project that we're doing with MAN and many others, we're looking at that whole system, and I know that the MAN are designing this, and this is another important thing in terms of discussing the transition from one fuel source and fuel system to another one in the future, is that MAN in this context have proposed to use the same basic engine for an LPG, which would be fueled by LPG, and just converting that over to ammonia. But that's something that we're getting involved with, obviously from the standards perspective. But I don't know to what extent and how far we've gone with it. But we're certainly in there in that discussion for sure.
Okay, well, if that's it, ladies and gentlemen, I'd like to call on Graham Taylor to